Okay, so let's get back to the business. Let me share you my window. There we go. So I managed to change the links. Links what I had missing are broken. Shall we first actually take a look at the what we are going to do? So on the assignments, actually there are some instructions how to do everything. And now the instructions link should work. Read the instructions. Okay, general information. Exercise instruction, excellent. So that works. So practically these exercises are for Octave and MATLAB. On all of those topics what we have about we have 6 different topical exercises, and basically I hope you have installed the Octave on your computer, and with some toolboxes. There are some the information toolboxes you need. You basically need the control toolbox and signal processing toolbox for the Octave. If you are using MATLAB, depending on the version, you should have the digital signal processing toolbox installed. If not, you might want to start working with the Octave, but usually the signal processing toolbox is the most common toolbox. If you are studying in Metropolia premises, we do actually have the this not campus license, but it's a license which works in some of the laboratories. It's the what is that called? It's a Flex Manager based license. Okay, in some exercises you actually need the secret number, SSS, which is not that secret. It's the last non-zero digits of your student ID number. So example, here I have the 3 last digits would be 604, but you take off all zeros, which means non-zero, then it actually is the 764. This is just to prevent any too small numbers. Just a moment, I need to get a look at the chat window. I couldn't install packages on Octave, it just gave me error message. Okay, you need to first load these packages. So the instructions are, I think, in this document. Hey, wait a minute. No, it's not on that document. Instructions actually are on the video. You need to, okay, on the beginning I will show you what I have done. Before loading them, you need to actually install them from internet. Okay, so working instructions. Start. Octave, log into Google account. Okay, this is optional. If you want to work with some of your classmates, that's fine. Or actually, I recommend it, since 2 or 3 students can actually work together more efficiently than just one alone, I have noticed. So you can help each others. That's certainly allowed or recommended. Help each others, and basically it means that you can then return the or have one single file that you all return. Okay, that's fine. But if you have a Google account, that's basically the, well, you have the Google account, yes. That's the easiest way of sharing the documents. You can also share the documents using the Microsoft cloud services, but the sharing in Google is so much easier and it works every time. But anyways, it's up to you. You will be actually returning the exercises either in Word document format or PDF in any case. But to co-work on the same exercise sheet, you probably want to share it and just edit one of them. Okay. Some obvious things. What else is important here? Attachment files. Okay, you will be returning one single file, meaning that if you need to return some other information like voice or other sample, different file, it must be a working link to a cloud service. Okay, what else? If there are mistakes, I will give you some feedback on Oma. But the if it's acceptable return, you cannot improve the number anymore. Not possible due to degree regulations. And then there are something like 30 students. If I start giving you too many chances of fixing errors, it will sound like a little bit too job for a simple-minded guy like me. Oh, okay. But however, do the corrections to your own records. Okay, and then if you don't hear anything about me, your exercise was okay and partial grade, you can find it from Oma assignments. I give you some partial grades there. Or another could be that I have not checked yet. I wait usually until the deadline has passed. And this is Friday deadline, meaning that I will start working on those probably on Monday, unless it's really bad weather on Friday. One possibility is what I try to avoid. Please try to avoid that one too. Do not copy. I have been student myself, you know, long time ago. So I know I've invented all the copying methods. So don't copy somebody else's answers. You can work together, then you have practically the same file. That's fine. But if you are, say, tempted of copying things, I'm pretty good on finding those, and I have some really evil ways of punishing. Yeah. All right. So, just a moment. Do I have the participants list somewhere? Yep. Okay. So the most important part of the exercise, this today's session starts now. Let's go and take a look what the template looks like. Exercise 1, signals. Some things to do. If you are already logged into the Google account, then you can actually make your own working copy. Do not try to change this when you cannot. This is my file. But clicking here, make a copy. After that, actually, this is your personal copy that you can edit. Every year I will get few of the students try to copy or try to change my document. No, it's not possible, but make your own personal copy and put it somewhere in a good place. Next, what you do is to mark your names. For example, here I would mark Antti as a student. Okay, you don't need to mark that one, and your personal SSS number, and this is my working pal here. Oops, image, my working pal's name there. If you need more, just add one more line to that one, but maximum 3 students. Okay, after this I would do the following. Share this document. Oops, share it with this document to, for example, I will share it with my working pal, which is me. Okay, as an editor. Okay. And here, let's do this exercise together. Something like that. And okay, share anyway. Yeah. Please use the Metropolia accounts for this one, but I have only one account, so I cannot show you that one. Demonstrate this one. So basically, after this, you and your the working group actually can edit this. Okay, this was quite obvious. Probably you have done it already. Okay, if you are using Octave, you need the Octave packages. Okay, let's see what kind of Octave packages. Okay, you need these. Control, signal. Okay, you don't need image and fits actually. Yeah, so control and signal are the most important parts. And basically, this is the command you should use. Package install, so on Octave command window, package installs -forge and then control. Package name, for example, here it would be just the control. Okay, that's how you do it. And after installing, you would do the package load and then control. And the same thing for the signal. After that, it should work. Okay, there we go. So I just put on the chat window that command package install -forge control, and the same thing for the signal. And after that, basically, I'll show you more on the Octave how to proceed. Okay, and then when you start working on the exercises, basically you will just write the answer on this column. The first one is for just an example, and for example here, create an index vector for -3 to 14. Okay, now we can actually start the Octave and see how that one is done. On the Octave, actually, you want to open the GUI, Graphics User Interface. There's also for historical users that CLI, which is just the client. Okay, does it start? Interesting. Very interesting. Nothing happens. Why nothing happens? there we are. I was just too hasty. Okay. So the octave, when you start it, it looks more or less like this. I have expanded the enlarged the fonts here just to make a better the visibility for you in case you are watching this one on smaller screen. When you open it, I installed that one, was it yesterday or day before, sometime this week anyways. So I think this is the latest version, is 5.2.0. But anyhow, nothing has changed for a few years for basically for this to make to use on this particular course. I think the first time Octave was used for this course was something like more close to 10 years ago. And these exercises haven't changed that much. They are not using any fancy new features of Octave, but they are focusing almost solely to the only to the fundamentals of digital signal processing. So I try to keep this you know, learning of the tool as minimum and concentrate more on what we are doing. Okay, one thing to do on the beginning, as you can see on the command history, I have installed the control package, and I also have installed something else. I've also changed the directory and stuff like that. But anyways, let's edit a file. It has a nice text editor, and there's a file called Octave RC. .octave RC. This file is actually called just before this program actually shows up. So basically the script, this is a M script that is executed just before it gives you that command window here. And here's an example what I have there. You need to install these packages, external packages, only once. So that package install dash forge control, what I have here, is done once. But after that, in order to use them, you need to load that package to Octave. And this is one good place to do it. Okay. So if you have installed any packages yourself here, then you need also to load them. And these two packages you will be needing: load control package, load signal. If you don't have that on your Octave RC, then basically you should edit those. After that, why it doesn't actually didn't execute that? Strange. It should have actually executed this. Very strange, but anyways, I need to figure out what is going on here. Okay, another one. When you are working on the Octave or exercise, it's nice to directly start on the correct directory. You should actually have this change directory command at the end here. Then it should go there directly. I need to figure out what is going on here, since evidently this current directory does not match what I have here. But anyway, so let me just run that one. Okay, so there we go. So Octave RC should be edited. So that's the that's basically the startup file, which didn't work in my case. Maybe there is some changes done lately. Okay, so so we have the current directory and directory viewing here. This one window shows the workspace, what we have on the variables and such, and then we have a command history. Command history is quite nice, since basically there you can just double click to run a command what you already have done. So if you have some commands that you repeat, you can just click it from the command history. Let me change this a little bit. Arrange the windows. Okay. At the end of the session, I will be also saving my command history. And for that reason, I will clear that command history. There. Start from scratch. Okay, so what Octave is, it's quite similar to, well, almost the same as MATLAB, except it's free. It's an academic project, which means that it may have some features, and definitely it does not have the same toolboxes as the MATLAB does. The toolboxes are totally different. This use for Octave is more on the academic world. MATLAB is mostly for industrial work, meaning those toolboxes are made so that they are efficient to use, so time efficient to use. So there are plenty of good toolboxes to make everything simpler, and they are it's just great package. However, we will be learning the fundamentals using the Octave. Okay, so let's start from the beginning. So I think every one of you have used already MATLAB at some point on one of the mathematics courses, I think. Am I correct or am I correct? Anyone? Have you used MATLAB? Yes, you have done. Okay, good. You know how it works. So if I type, for example, a command like nn equals bracket from -3 to 14, you know what that does. So it's a auto-indexing, and those brackets are actually not needed. Not needed. There we go. So it gives you the numbers from -3 to 14, which you can also see from the variable editor, like that. Similar to MATLAB, it also has the variable editor. Okay, and if you put the semicolon at the end, it doesn't print out, and if you put a comment, okay, something like that, it still does the job, but doesn't print it out. Okay, how to actually work on the sheet now? I can copy my working command here, and let's go to that document. Create an index vector from -3 to 14. That will be the correct command. Right, copy paste. There. Just make sure that you copy the correct commands. So copy pasting on this case is very allowed. Actually, it is recommended, so that you have tested the commands how they actually work. Okay, then the fundamental functions. We have the delta function. I will call it dd. dd is equal to, okay, we just test if n equals to 0. Double equal sign is the testing if it's a 0. If you are using single equal signs, it's a asserting operation. So basically something gets a value of something. Okay, a variable gets a value of a constant. But double equal means it's equal. And basically this, in principle, it should give me the Boolean, like, okay, logical values. It's a good idea actually to typecast these to double, which is the fundamental variable type in MATLAB or Octave. Typecasting, basically it's meaning it's forcing the data type. There we go. Now dd is double, and now we can use that value as the something to plot or something like that. Okay, how about then delta with delay, meaning delta n minus 5, for example. Okay, that actually is quite simple. You just have the dd5, for example, here equals, again, typecasting of nn minus 5 is equal to 0. And it doesn't hurt to have enough of these parentheses to make sure that nn minus 5 is the calling parameter for delta. There we go. And now we have another variable here, dd5, which has number 1 at index 9. Great, although this kind of tabulated data is not that much fun as plotting them. I think we have, I need to check that one, help and stem. Do we have a stem plot? Oh yes, great. There is a stem plot. Stem actually is the way to plot this kind of short data vectors. Stem, horizontal information and vertical information. So that's the delayed delta plotted as with circles. Okay, there we are. That's the plot. Haha, great. We can plot things, and that's how the delayed delta function looks like. So there is a time delay of 5, so basically it happens at time step 5. So for example, 5 seconds from now. So it's a delay, happens on the future. Okay, then that's the fundamental function of and how to plot these things. Okay, let's take a little bit back and a closer look on this figure, since I'm not too happy with the figure yet. there are a couple of things that are not that nice. It does not look that nice. I would rather have the data such that it does not actually touch this drawing box. Now on the edges, there's no data on the middle, everything is on the edges. I don't personally like this one. It looks bad. And since this is a figure, basically I would rather have it such that it's the figure, the horizontal scale is the same, a little bit wider than my sampling or subsample, the sampling range, the window I'm looking at, and then the data actually should start from a little bit negative, going to more than 1. It can be done by simple command axis, horizontal axis from minus 3.5 to 14.5, vertical axis minus 0.2 maybe to 1.2. Now the data looks much better, at least in my view. In addition to that, you probably also want to put a title there, title my plot, whatever that would be, and x-axis label, x label, oops, index n, and y label value, something like that, and my picture looks like this. Okay, good, all just typed in. You will be needing these commands actually on this exercise, and how to then, wait a minute, how do I get the there. Then how to use this picture in your document. Save as bitmap. Actually PNG would be better, so let's go somewhere here, and I'll just mark here fig1.png. Save, and then you can actually go and go to your documents, result of exercise fig1. Looks okay. Then just take this exercise, and where I have the figure, whatever figure you need to put there, just, I think you can simply drag and drop it there, maybe. Yoo-hoo, it works. Now you should actually pay some attention to the size of the figure so that it's readable. But on this exercise, I think these indexes or this font size and such are just fine by the default. Okay. There are some. Okay, now you basically should be able to do the previous vector to generate unit impulse function, 3 time step sample delay. Yes, previous create the index vector, unit step. How to create unit step? No, I want to move it a little bit. There we go. So unit step is quite same as this delta. By the way, if you click the start of a command and then arrow up, it shows you all the commands you have made, up and down. So you can start from one of these and just edit. UU equals that index is greater than equal to 0. So that's the unit step function. So again, we are just testing using, we are using the definition. So if the index is greater than equal to 0, then it gives a logical 1, which is typecasted to double type, meaning 1. Okay, so that's how you create a unit step function with the fundamental functions which comes either with MATLAB or Octave. Okay, so practically those were the hints for the first 4. Okay, then the next one would be sampling a sinusoid and also multiplying signals, signal multiplication. First, sampled functions. I will use example. We have x of t, meaning the time space the continued time space signal would be something like something like that. So exponential decay function. Continuous meaning that it's at time 0 it's gets value 2 and basically decaying further, but also it has also the left hand side. Okay, so exponential decay starts from -infinity. Okay, how to create that one using the time steps here? Well, we need the sampling time, TS, 1 millisecond. Does it work here? Oh, who cares? Oh, I do care actually. Let's make that one, for example, 10 milliseconds. So which means actually the sampling rate is 100 samples per second. It should be actually marked as like that one. 100 samples per second the sampling rate, or 10 milliseconds sample time, and remembering, okay, that x of n equals actually then x of n times ts. That's the sampling. How you do any continuous time signal to sampled signal. Okay, there, xx equals, we have the 2 times exponential of minus t equals n times ts, and ts was 10 milliseconds. let me start over and first make that. Make some constants. TS 10 milliseconds, FS equals 1 over TS, just for fun. Okay, and next we can do the sampled vector 2 times exponential of minus n, our index, times TS divided by 10. So I am sampling it here. Okay, and then stem NNXX to see how it looks like. Wow, oh, it's almost constant. Okay, I think I need to adjust it so it makes a little bit nicer looking. 100 milliseconds. 100 milliseconds. Just adjusting a bit. Yeah, now it's a little bit more interesting. Maybe even make it so that it's really showing up the decay. Ah, sorry about that. I'm just playing with the numbers here. Let's keep that one at 10. Fat fingers. Engineering notation, and then I will just change this. Oh, divided by 10. No, divided by 0.1. Okay, that's better since now it's the time. Okay, yeah, that makes more sense. Stem. Yeah, now it looks like an exponential decay, which could be a sampled RC high-pass filter signal, except it starts on wrong place. It doesn't start at all. It basically starts from minus infinity. How to start a signal, for example, at point 0? I will take my new, oh, not mu, the Heaviside function, sampled Heaviside. So unit step function, and we use that one to start the signal. So xs uu equals to xx dot times. So this is actually a cell-wise product, so signal product. Same, since these are vectors. If you do a vector product, then you need to have the vectors on different directions, and then it's not the same as what we are looking for. We are looking for a cell-to-cell or the vector component-to-component product, signal product. This is for multiplying signals. And let's stem again, XXUU. There we go. Haha. Now we have a signal which starts at 0. So this could be a sampled RC filter, RC high-pass filter output when you hit it with a step function. Great. Good. Something useful. Exponential decay. Okay. Sometimes you want to add random noise, or in this case actually on the exercise you will be adding a time delayed stuff there, but anyways, you at some point you also need the random values, and that's actually the same as noise. If we calculate, for example, EE equals to rand n size of XX, this calculates a vector of, okay, it doesn't fit in my screen, I think, vector of random values same size as XX. How random are random? In this case they are random enough. Where's my, wait a minute, I didn't. EE. There I go. Okay, random values are more or less random. However, it's pseudo-random values, which means that it's mathematically calculated random noise with some spectral characteristics, like this is white noise spectrally, meaning all the values appear at the same rate or constant rate, but the values are distributed as a normal distribution. But they are always calculated starting from the same seed values, meaning that if you typed exactly the same comments as I did here, you will get exactly the same numbers. There are methods to randomize it, but for this course any random numbers will do, as long as they are as long as you are using them correctly. So now we have these random values that we can add, for example, on that XXUU plus EE. Added noise. Ha! Lots of noise. Maybe a little bit too much, but anyways, there's the exponential decay, but our noise is quite high here. How high? Okay. Signal to noise ratio. I calculated using this definition. Variance of signal. Since I generated myself, I can calculate the variance and also the variance of noise. So this is how you check your signal to noise ratio when you have generated the data yourself. Not too great, so it's negative signal to noise ratio, meaning that you have more noise than signal. And from that picture, actually, what we had, I can easily see that. So almost -6 dB, meaning 4 times noise power than signal power. Okay, anyhow, if you want to match your signal to noise ratio to some certain number, what you can do is basically scale the scale. Oh, no. I hate when that happens. signal to noise ratio. Calculate, for example, if I scale this noise with 0.1, that actually brings me already 20 dB higher. Yes, of course, 10 times more. So if you were looking, for example, the signal to noise ratio of about 20, you can either kind of find the correct factor to multiply your signal, or you can calculate it from the definition. So if I give you the signal to noise ratio target, you will calculate from pen and paper calculation what is the number you need to use to multiply your noise to achieve certain signal to noise ratio. Here I do it the brute force way. Okay, one more time. So roughly that one to get signal to noise ratio of 20. So basically I can calculate that one again, 0.0053 times EE. Oh, no, not 00. There. Now I have signal to noise ratio as required 20. Stem. Oops, not that stem, but the other stem. And then there you go. Okay. Looks less noisy. Good. So that was the signal to noise ratio. How to use it, how to multiply signals. What else you need to know today? Stem blotting, data sequences. Okay, and the last one is sound sample. Okay, the last part is sound sample and saving it to the file. Just bear with me a bit. So this is the fun part. No, generating sounds. So are you tired of your phone ringing sound, since everyone else has similar? At least I am. I used to have a really fancy sound generated myself, but then I have changed so many times these phones that I don't care anymore. I don't care about my own ringing sound anymore. But anyways, sound sample. Let's start everything more or less from scratch. And Nokia's vibrating is good. Yeah, Nokia's vibrating is good enough. Or actually, it would be nice to have a Nokia phone on some other, a Nokia tune on some other phone, Samsung phone. Haha. Okay, but from scratch. Let's start from scratch, meaning that I will define my sampling rate over. Remember, when you are doing something like this, you are overriding that previous T of S. Currently T of S is 0.01. Well, let's start from F of S. Okay. So CD quality audio is 44.1 kilohertz. There. That's CD quality. Meaning T of S is 1 over F of S. That's a sample time. I always calculate these in any case, so just in case, you know, whichever I use. Okay, and then we have to define our window. What size sound we want to have. For example, if I want to have 1.5 4-second long sound. I can do it by defining a sample time vector. So this is actually directly n times ts. I start from 0 time with time step of ts up to 1.4. So that's another use of that colon operation. If you have 3 values, then it actually means from step size 2. It makes that vector, and basically this tt is then basically as n times ts directly. Sampling time vector. There. And sinusoid would be nice. That's a good place to start, and then we can modify it a bit. So time step, and then we just generate the sound. I call it S is amplitude times just as arbitrary amplitude. Sinusoid 2 times pi times some obnoxious frequency, 440 Hertz is just fine. So that's a singular frequency, 440 Hertz. Anyone playing some musical instruments, 440 Hertz is the basic note A. That's how you tune a guitar or something like that. And then just 2 pi ft, which is our sampling vector. So sine 2 pi times f times t. That's our x of t, or here s of t, continuous time. So we started from that. Yeah, that's the sound. Now I don't know if that sound, if I can play it here. Let's see. Maybe. Sound. Yeah, excellent. It actually plays. Good. Sound, as long as everything works as they use, and that they must work. Okay, sound, signal and sampling rate, fs. There we go. Did you hear that? Maybe. Okay. Good. So that was 440 Hertz. Not. I wouldn't call this awesome, but thank you. Thank you. That was my original hit. Original hits of Antti. I will just play a little bit with this one, since I can easily modify it a little bit more. Yes, let's make Nokia soundtrack. Yes, let's do it. A little bit of the modification would be to have some decay for that one. SSDD equals ss dot times exponential. Haha, exponential. So it's a decay function. So it's like starts with high bang, and then it's just this thing goes lower, minus tt, but then I need to probably divide it by 0.01 at the times constant. On 10 milliseconds it goes factor of 1 over e, which is about 40 dB, maybe like that. So that's the decay. Sound SSDD. Oops, a little bit too fast decay, I think. Okay, that resembles a piano. faintly, but still. So practically this is how the synthesizers do things. All the tones what we are playing basically are related to the this logarithmic frequency scale. 440 Hertz is basic note A. Then each half note is basically 2 to the power of number of half notes in between divided by 12. There are 12 half notes in octave. And then basically you can find the notes from there, each note. And then you can modify the signal by adding decay. There's also the function called sustain in this old-fashioned synthesizers and so on. But anyways, this is how you generate a sound. And of course, let me add here a little bit of noise, plus 0.1 times random size SS. White noise added to this one, and having the exponential decay. Okay. More modifications. I could already use that one as my say notification for incoming mail or something like that. But anyways, this now you have limitless chances of making your own sounds. You just need the good imagination and think of the what the audio envelope would look like for that signal, what you want, and what is the basic signal there. Okay, good. One more thing. The last thing for my session here today is to show the how to save audio files. I think there's a command called audio write. Yes, there is. Audio write, file name, data, sampling rate. Good. So how to save this one is simply you write audio write ssdd, file name first, sample.wave. Actually this function can also save AU and whatever. There's several different formats it can save it, but give the wave file is just fine. It's PCM coded audio file, then SSDD, and then the bits. How many bits? 16 bits should be just fine for that one. So it's CD quality. Right. Oh, no, bits. Sorry, that was FS. Haha. Bits was the okay. If you want to change the bits per sample, you need to give it a pair. Okay, for example, like this. This is required, but the optional part is, oops, not that. FS bits per sample. And how many? 16. But that was also the default. Anyways, the okay, this help files are getting much better than this. Is better improved from last year, I think. the help files used to suck with the Octave, and that was one of the good reasons I used MATLAB more. But now these help files actually are helping. Good. It has the full documentation of the functions. Where to find the functions if you don't know, if you know what to do but don't know the function? Well, there is always also the documentation, online documentation that you can search if you know what you are doing. But anyways, today's stuff you can just use whatever I did here and just do the thinking yourself what it means in your exercise. Anyways, now I have that one audio sample, and let me then just check it first. Okay, sample. Yep, it works. Good. After that, how to include that file on your answer. Only single answers actually are allowed. Here's a hint. Provide a link to your sound sample, meaning that you first need to go and do something about it. So my favorite place is to make the go to my Google Drive, copy that file to Google Drive, upload completed. Okay, where's this? Oh, I think it's always on the wrong place. Sample. It seemed to, yep, it seemed to work. Good. All right, and where's sample? Okay, this is important part. You need to set the sharing correctly, since it will be a link that I will be opening. You can use this restrict, the only people added can open this link, meaning that, okay, let's see there, use the Metropolia Ammattikorkeakoulu organizational, or actually even better, anyone with the link. Anyone with the internet link can view that file. If you don't share it, I cannot test it, and you lost 1 point automatically. It'll never come back. Okay, so now I think I copied the link, did I? And then just, oops, there, copy, provide here. Oops, I didn't copy the link. Ah, this was bits per sample was copied, not that one. Where's my, there it is. Get link, here we go. I shared it, but didn't copy link. Copy link, there, good, done. Anyone with link can view, and here we go. It does not hurt to test this one again before you submit the file. Test that it works. Yeah, it seems to work just fine. Okay, so one more thing, how to return the exercise. It was a single file. If you are working as a group, everyone on the group must return the file. This is just because otherwise only one will see the this grade or partial grade. How many points did you get? And only one gets the feedback. So if you're working together, then I will give you the same numbers and same feedback to each one of you. It's just for the workaround for these group returns. And then basically I can open it as PDF or download it as PDF document. PDF, I think it's better than the Word doc. Okay, where does the file save on MATLAB? Yeah, MATLAB, it goes actually on your working directory. Yeah, got it. All right, there. Where did my PDF actually go? Oh, yeah, it goes to my down. Of course, it goes to mine. Come on. Where's my? Maybe it goes to the downloads. Yep. Copy of exercise 1, exercise signals.pdf. Oh, okay, it's already on my preview window. And before returning the file, again, check that everything is okay, that the figures are there, your answers are there, your link opens preferably in an anonymous browser, then you know that it's available for everyone, not just for yourself. Wow. Okay, good. So that's all for today. Okay, there's a question. So if students work in a group, an identical file can be submitted by all. Yes. In that case, identical file is okay. However, you can always make tricks if before the deadline passes, you notice that there was a mistake, and then you edit only your file. You will get the points, not your fellow students. So try not to do that, to annoy the fellow students. I'll be basically looking at those as individual, individual returns. But anyways, everyone must return a file. But okay, so that's all for today. What happens next? I'll be hanging around online, keeping the chat window open, and also keep this keeps showing this sharing my screen. I will turn off my muting my microphone, and I will save my command history and basically giving it into the putting on the documents for this topic 1, exercise 1, the command history file. I will also start uploading the videos. There will be 2 videos. One is for the lectures part, which is about 1.5 hours. Another one is for this laboratory part, which is about 1 hour 20 minutes or 30. Yeah, 1 hour 20 minutes. So those are long. That's why I actually cut those in 2 parts. But those are available maybe tomorrow. Maybe tomorrow. I will be actually uploading those as the publicly accessible the videos to YouTube on my channel. There's a channel or basically a list. I made a list for this particular course. You may want to subscribe yourself. Anyhow, so if you have any questions, just put them on the chat. Otherwise, work on the exercise. The deadline is next Friday before the session start. I think it was 9 AM deadline, or was it 10 AM? Anyways, before the, I'm expecting the returns before the next session on next Friday starts. Okay, so I'm actually now shutting up and start working on my files.